Yeah. So, welcome to another edition of our weekend get together to discuss AI and machine learning. The title we started looking at since last week, we said taking benefits of machine learning modeling, irrespective of your background. Irrespective of your background. So you don't have to come from computing specialization before you can use AI machine learning. It is a technology that is taking the world by surprise. A lot of positive potentials. So, of course, everything with positive side also has its negative side. However, that is why people of morals also need to get involved. People of conscience has to get involved so that the negative utilization of AI does not get proliferated. Rather, we see how we can use it to benefit ourselves and humanity in general. And as they say, the only thing necessary for evil to triumph is for the good people to do nothing. So people who think right, who know, who can differentiate between the right and wrong, so can then be able to key in and see, okay, how can we take benefit of this technology positively while discouraging the negative utilization? That is why in our own training, we encourage what we call ethical and responsible utilization of AI. See, this is always our watchword that we should always think of what we want to use AI for. It's a technology that is so powerful. If it get to the wrong hands, it can do a lot of damages. So AI, we encourage us to always think of, and there are so many areas we can put it into use in positive ways that can benefit ourselves, our system, our profession, and even the entire humanity. So this is our work here that we say always think of how can we use it ethically and also responsibly. So today we are going to continue with what we discussed last week, where we said that making sure, see, it's something to be doing, something that you think is correct. Oh, it is the right thing, but are you doing it right? Are you implementing it in the way it should be done? That is why we titled it, Making Sure You Are Doing It Right. So we started the discussion last week and we're going to continue with this. It is under our clarification series. We call it important clarification series. With the team, always let the data speak. So we're in the world of data science now, world of data science. Let the data speak. When you hold on to the data, that data has some information to be passed across to you. But if you don't do it right, you may miss silent information from the data. Because we want insight from those data. So are we able to get it? If we do it the wrong way, then you may miss some of this very important insight from the data. That is why when you use machine learning for data analytics, we always stress the need to do it right while letting the data speak. We've often mentioned that the machine learning modeling building block or framework is an iterative process. Iterative process in the sense that you have that liberty to go, this is your data, this is the algorithm. So here we have the data preparation, we have then the feature engineering. Both of them are all referred to as pre-processing stage. They all take place at the pre-processing stage. You prepare your data, you clean your data, you do some things there. Then you move to this stage where you have the algorithm, we call it data modeling. You use the machine learning algorithm to model your data, and then you have the performance measure to be checked. Is this satisfying for me? If not, you can always go back here. You can go back here. You may have to go back to the data preparation and feature engineering stage altogether. And you keep doing this, going back and forth until the model reaches a satisfying performance. This is the target. How long are we going to keep going back? Until it reaches a satisfying performance. What is satisfying in your field may not be satisfying in another field. So that performance requirement has to be defined. That is why when you have competitions these days, you see people putting a particular target. For example, the popular Netflix competition some years back, they put a price. If you can improve their recommendation system by 10%, you get $1 million. Just 10% improvement to what they have presently. And they provided the data set. And people struggled, they couldn't get it. Until teams came together and combined their work together in what we call ensemble, and they were able to achieve that 10%. So they claimed their money, and then they can share it among the teams. That is the power of togetherness. That is the power of ensemble, which we've discussed some of those technologies, techniques before. So then we are going to now see at what stage do we think of, okay, do we keep going back? What do we do before we proceed? These are some of the stuff we want to discuss. Again, we quickly let us know that there are different angles to solving problems using AI or ML-based models. I categorize into two. I said to the people from diverse backgrounds. You are not from computer science. We have people from computer science related backgrounds, software engineering, cybersecurity, whatever your area. And then we have people who are not from those computing related areas. You just think of maybe your own daily activity, maybe a medical doctor, maybe an engineer. See what you think you could do better. So think of it. We recorded in the past some of the application area you can think of. We can check our archive, our videos in the YouTube channel, where there was one we called "Why You Can No Longer Ignore AI." Why you can no longer ignore AI. One of the volunteers about the admin people should please help us post that video to the chat so that people who are new can take it and watch it later. You see, there you see a lot of ideas from your area, from different backgrounds, how you can think of, because there's practically anywhere you can generate data, you can benefit from AI and machine learning in a positive way. Yeah, without losing your job. Because people say, oh, AI will make me lose my job. No, AI will make your job better, will bring more customer to you, will make you do your work better. So I always look at that positive side, not the negative side. The negative side often affect those people that runs away from AI because AI will finally catch up with them and it will take over their jobs. But rather, don't wait for AI to catch up with you. Improve yourself, reskill, upskill, get your work done better using artificial intelligence. I see as more of support system, not a replacement system. Replacement system, I don't advocate for it for now. We are not yet there. We have a lot of people that needs to work. We should think of how we can use AI to improve our service delivery while retaining jobs as much as possible. And it actually creates a lot of jobs for people who are able to reskill, to upskill as soon as possible. And as I used to give in some of my presentations, the case of a photographer or an event coverage guy who specializes in using helicopter to do aerial covering. When you have to cover an event from the sky, you have to rent a helicopter to be able to do the job. Very risky. So very, very risky. And you can only do one at a time. But if that person quickly key into AI, learn how to program drone, it can actually, it can deliver like it can cover several events at the same time using drone without leaving its own room. It will be covering several events, several kilometers away. So it can make more money, it can make more customers happy. So that is what I mean when I say we should always think about the negative aspect of it. Think of how you can use AI or machine learning to improve your skills, to improve your work, to get your service delivery better. That is what I see from in AI as far as we are concerned. Of course, there's the negative aspect of everything. So once you think of what you can use it for, as somebody from different background, from AI, from computer science, Then brainstorm about your area and your specialization and your interest and see how you could utilize ML modeling towards improved outcomes. So once you are done with this, then further think of how you can improve upon your earlier achievement. Once you have done this, think of what you can do to improve what you have done earlier. And then the cycle continue. For those from computing related field, clearly you have a lot of opportunity in your hand. As they say, computing is the pivot of the world civilization. So the whole world is looking up to computing field to see how they can solve their problem better. So cybersecurity, AI, software engineering, so many areas. How can you, what are the areas that needs their improvement, that need your service? So we have to be proactive. As people from computing field, you don't need to wait on somebody come and tell you, hey, I will need this thing. Reach out to people, educate them. Sometimes your potential customer does not know what they need. That is a policy in software engineering when you are gathering the requirement. It is often believed that sometimes customers don't exactly know what they need. So you have to find a way of elucidating and getting their requirement. Let them be aware of the possibility that you have with you. So think of area that may benefit seriously from what you have, then deploy machine learning modeling there. Further, think of how you can improve upon your earlier achievement through producing more advanced machine learning algorithms-based solutions like hybrid or ensemble modeling. And then you can even also think of developing new machine learning algorithm, totally new one that has not been used before. Yes, because you are at liberty to use existing framework that has been used to solve a problem. You take it to solve another problem. It is considered a new system. Because the fact that you use an algorithm and a framework to solve data from oil and gas doesn't mean it's going to solve it for medical. So if you are able to reproduce it in medical area, it is considered a new idea. You have to get that right in modeling, in machine learning-based modeling. However, sometimes you want to come up with totally new algorithm that has never been developed before. It's also part of it. People from other backgrounds may not have that capability yet, but you have that advantage. And as they learn, they can also develop their own capability to the point that they can also even think of creating new hybrid and new ensemble that has never been used before. So like we try to make it as simple as possible, as easy as possible with the no coding approach. No coding. Coding is what usually drives people away. People are scared of, I don't know how to program. You don't have to program to build AI or machine learning model and deploy it successfully. So it is possible. So you can build totally new system from the scratch and then deploy it as the case may be. So these are from the two points of view that things can be approached. People from different background, think of how you can use it. People from computing, think of what you can solve problem for people. Problem you can solve for people. New solution you can put out there. So now we're back to the iterative machine learning modeling scheme. Now, with one we're going to look at today is the one we call the modified iterative machine learning modeling framework to support let the data speak. You see, here we've added a couple of stuff there. You can see here we have data consolidation, we have data cleaning, we have data transformation and feature engineering, we have data reduction. These are some of those things we can do under the data stage, data preparation, data pre-processing, and so further, feature engineering. Look at several, and you can see that each of them is having etc., because there are so many lists. So do we have to do all this before we proceed? That is big no. You don't have to do that. And that is what we want to stress. You don't have to do all this. There are so many pre-processing that are possible. But you don't have to do all this. Otherwise, you never do anything. See? So in that sense, how much is necessary? How much do we do? And move on. So once you have your data, you do the most basic of the pre-processing. This is the beginning. Your data, you are getting data from different sources. You may have to do data consolidation. Data consolidation means after collecting the data from branch A and also branch B of your company, you need to add them together. You need to merge the data together so that you want to be able to have the prediction you want. And sometimes, no, I want to do modeling for different branches. I want to predict the number of customers that will come to branch A, number of customers that come to branch B at so dates. So I want it separate. That's okay. You go out with it. You don't need to consolidate the data. You don't need to bring them together. That's why I said some of these things are optional. You need them, you do it. You don't need them, you move on. So I have my data. You integrate, unify, as the case may be. But once your data is in the format that can go into the system, you are good to go. Your raw data that is coming may be okay. So the only thing that you need to do is any pre-processing that will not, if you don't do it, your model will not work. Then that becomes compulsory. For example, when you need to undo other data cleaning, you can see there are so many activities or techniques for data cleaning. So many activities. You don't have to do all of them. Otherwise, you will never finish up. It's not only that you will not finish up. If you do too much cleaning, when you wash your clothes too much, if you use the wrong soap, the new clothes can become very whitish. You destroy it by too much washing, by too much cleaning. The same thing is applicable in data. When you are cleaning your data, you have to be very careful. Otherwise, you may end up carrying out what we call data mutilation. You did so much cleaning that your data is nothing but fake data. You have cleaned all the good things in the data set. You have cleaned them off. We have to avoid that. That is why the principle of let the data speak says that try as much as possible to retain the data in its original form as much as possible. How do we do this? How do we ensure this? So once you load in your data into the modeling scheme, modeling environment, run the model. Don't forget there's a principle of start with the simple algorithm, with simplest algorithm, one of the simple algorithms first. Don't go for sophisticated algorithm. So select an algorithm. Let's say we want to start with KNN, K nearest neighbor. A very simple algorithm. We've discussed it several times and you have the videos on our platform. So you use K nearest neighbor, you solve the problem, it is doing fine. You check the performance. Is it okay? Is the performance okay? That question has to be asked repeatedly. Is it okay? If it is okay, congrats. If it is not, then you will have to go back. You see, go back. So when you bring in the original data set, because somebody may be asking, because some people, once they get the data, they do the missing value treatment, outlier treatment, reduce noise, remove duplicate, ensure consistency, so many things to do. Yes, there are some that are very important. You see, however, once you have the data, let it go through the system. The most important I can say, almost you may not be able to do without it, is the missing value. If there are missing value in your data, some algorithm will not work. For example, support vector machine will not allow you to run its system if you have missing value in your data set. However, with decision tree, you can run with missing value because decision tree has an inbuilt mechanism to deal with missing data. So in that sense, that means you can run even a data set, the data set we having missing value can still be modeled using decision tree or decision tree algorithm family, like random forest and all those decision tree oriented and hybrid and ensemble. So you don't need to do even missing value treatment, which is very, very important. So that's why here we can say that handling missing value may be one of the most important data cleaning operation that you may have to go do. Because apart from decision tree and few algorithms, majority of algorithms will not work if there is missing value in your system. Therefore, let's agree that, okay, we do the missing value treatment. And there are several methods of treating missing value. Several methods. You may have to replace the missing value with the mean of each of the column. You may have to replace them. You may have to remove that particular sample totally. Because of our time, we can refer back to we have earlier sessions where we discussed how to treat missing value. You can check out the video on our platform. So missing value treatment. There are several methods of treating them. And which method is better? No one can tell. You let the data speak. See, that is why in data science application is better done in a team. Team. When we say team, yeah, team of 4, 5, and more. So that you could be able to experiment with different scenarios. Because missing value treatment alone is not one method. There are several methods you can try. So let each team member try out different missing value treatment and see which one is working for your data. Because the one that worked for your data you used last week, a new data from maybe a particular field, from oil and gas. This week, the one coming from medical laboratory, that missing value treatment you did may not work for this data. And that is what we call let the data speak. So you have to try each of those methods of missing value treatment on your new data. Tomorrow you have another data from another client. You have to try again with different method. Oh, this is the best missing value treatment that always work for me. It doesn't mean that it's going to work for your new data. Let us get it right. This is one of the principles that you have to you have to stick to ensure that you are not missing insight in your data. Now, so once you get, let's say we got the missing value treatment, we pass in our data. It goes to the data modeling stage. So in the data modeling stage, we have the default hyperparameters there. You run it like KNN. In KNN, for example, default parameter is usually k is equal to 1. And then the distance measure is usually given as Euclidean distance. Euclidean distance. That is how to calculate distance between two objects or samples. So with k is equal to 1 and Euclidean distance, check the performance. You build a model. Once you have data plus algorithm, the end result is called model. Let us get that one right also. A lot of people use this interchangeably. It is not correct. They use algorithm, they also call it model. They say, which model should I use? They are referring to algorithm. No, there's difference between algorithms and model. Once you add data to algorithm, then you undergo training. The outcome is called a model or hypothesis function that you have generated after the training process. So once you check the performance of this model, maybe it's satisfactory, luckily for you. How are you sure that it's satisfactory? You need to check up, except you are getting 100% in all the performance measures. Your accuracy is 100%, your precision is 100%. Every other performance measure criteria they are all excellent, super excellent. That is when you can only stop on your default value. Otherwise, you don't stop on default hyperparameters. You go back and check for other hyperparameters. That is why here you can see here I mentioned the hyperparameter. Very important. Hyperparameter tuning or hyperparameter optimization. So you want to check when k is equal to 1, okay, we are getting 95%. Okay, why are you stopping? Go back again, k is equal to 2. When k is equal to 2, run the experiment again, keep your Euclidean distance fixed. We got 98. Oh, great. When k is equal to 3, we got 90, 94. You can see it was 95 when K was 1, 98 when K was 2, and then it became 94. That means you have something like it was I, it was below, then it goes up, and then it goes down. So this is the best hyperparameter you are going to select. The best hyperparameter is at this peak period. We always look for the best. That is why hyperparameter optimization, hyperparameter tuning is considered an optimization problem. You always want to get the best of the best. So once you are done with that, let's say you are bringing in another algorithm like support vector machine. Support vector machine or decision tree, you do the same thing. Run using the default parameter. And then you go back, you check the result so that you can compare. Because in machine learning oriented modeling, we always compare. We want to see which one is doing better. A common mistake, let me clarify here. You see some people, they will use k-nearest neighbor default parameter. They will use support vector machine default parameter. And then they report the result. They conclude maybe k-nearest neighbor default parameter was getting 95. Support vector machine default parameter was getting maybe 86. They conclude, they says KNN is better than support vector machine. This is not correct. Your experiment is not valid. You see, you are practically you are actually lying against support vector machine. Not all default hyperparameters will work. You see, so you have to do hyperparameter optimization for each algorithm you are using. So as you have tried for k-nearest neighbor, try k-score to 1, k-score to 2, k-score to 3. You also check for Euclidean shape equation. You also check the other distance measure that is possible. Once you are done with that, you also go back to support vector machine and check for the hyperparameter optimization of support vector machine. Finally, you realize by just changing the hyperparameter value of kernel for support vector machine, changing kernel from polynomial to Gaussian, you are surprised that the performance of support vector machine jumped from 86 to 99. Meanwhile, you already concluded that KNN with maximum of 98 was better than support vector machine. That is why you have to exhaust that hyperparameter optimization. It's a must. It's a must. It's compulsory. You have to check different hyperparameter values and make sure you are selecting the best one. Check for this, change to this, change to this. After you have tried several combinations, then you come and say, okay, for this algorithm, this is what it can get for me. And if luckily you have gotten what you need, 100%, you are good to go. Remember, there are so many pre-processing we have not done here. You see, especially normalization. Look at data transformation. Normalization is still there. You see, we have not done it. We have not touched it. We are using practically the raw data. And it is better to let the data speak. Because data that will be coming from the system, they are raw data. So the one we want to use our system later, when you deploy your system to real life, it's going to work on real life data. So the closer your model data is to the natural one, the better. Of course, the idea of pipeline, but I will tell us some things later. Let me go there yet. So once you have the result and it's satisfying for you, you are good to go. Then you can report. Write your report, you are done. That means the system, this is what the system is having. However, depending on how difficult the data is, you may have to go back. Depending on the problem you are solving, there was an area where we made an inroad for the first time. We just achieved maybe 75%. We thought we are just starting. We need to go back and do some pre-processing more. The client said, no, we used to work with statistics. The maximum we were getting was 45. So getting 75 from machine learning is more than enough for us. Don't worry. We are okay with this. Deploy. Because they were surprised that from 45 they were stuck with, they were able to get 75. Even though to us, we are not yet done. So they are okay with it. They say it should be deployed. But to them, that is more than what they are looking for. This happens sometimes. But sometimes you needed to be at almost 100% performance measure, all rounder, before it's acceptable. So at that point, your hyperparameter optimization is the first thing for you to do. See, once you have done it for KNN, for support vector machine, and again, a quick one, hyperparameter, they are those parameters that will affect the performance of your algorithm. See, because we have, generally in computing, we have parameters. You see, when you have a function, we want to calculate square root. Say x or y is equal to square root SQR, square root of x, comma, decimal places. You see, this is a function in computing. We use it a lot. So we said y is equal to square root of x. X is a value to be given. We want to find the square root of x. And the decimal place for the result you are going to return should be, we give the number of decimal places. So I can have, give me square root of 50 to decimal place 2. See, this 50 is very, very important. See, very, very important for us. Without it, we cannot get the result we are looking for. We can compare it to the hyperparameter. The hyperparameter. However, these two is just number of decimal places. It does not affect the value of our result. It's just a matter of, okay, I'm not rendering them to 2 decimal places or 3 decimal places. So those parameters that does not really have direct implication or impact on our algorithm, we call them ordinary parameters. But those that have serious impact on it, we call them hyperparameters. So when you want to use, again, I give another example. When you want to use k nearest neighbor, KNN, I've written a particular function. K, I have K here. I have a distance measure, and I have also decimal places, DP. I have 3 parameters being sent to that function called KNN. The first one is K is 1. I'm sending KNN now with 1, comma. I'm sending it with Euclidean distance to be EUC, short form, Euclidean distance. And I'm sending 2 here, number of decimal places. So this one is hyperparameters. K is hyperparameter. Distance measure is hyperparameter. These are things that affect the performance of KNN algorithm. However, the number of decimal places is a parameter, but not an hyperparameter. So when you have to differentiate between parameter and hyperparameter, those hyperparameters, they have direct effect on the performance of your algorithm. The decimal places is only telling us, after you have gotten your result, make the result to be in 2 decimal places or 4 decimal places. They are inconsequential as far as the performance of our algorithms are concerned. So this is, so that I keep mentioning hyperparameters. So what is hyperparameter? This is what is hyperparameter. Those parameters that have significant effect on the outcome of our model. Not just a dummy variable like some parameter just tell us the randomization factor. How do random number generator number, maybe 2, maybe 3, or whatever you want to assign. So the hyperparameter optimization is the starting place if you have to do it right and you want the data to speak. So once you have tried the hyperparameter, then you record what you are getting. Are you closer to what you need? Are you still far away? At that point, you don't still need to go back here. You can see the first arrow says go back here. You can go back here to do the hyperparameters. You can go back, change the algorithm. Sometimes you may have to change the algorithm. You see, change it to support vector machine and do the hyperparameter optimization. Change it to Decision tree, change it to logistic regression. There are so many algorithms. Keep picking them. Maybe you see the one that is going to work for your data, because every data set comes with its own unique insight and characteristics. So an algorithm that worked wonders for you in your previous modeling last week, that algorithm may not work on the new data you just brought in. So that is why one of the principles in machine learning modeling, if you want the data to speak, is to start from simple algorithms. Simple one, KNN, decision tree. Before you keep going to sophisticated algorithm, we've had the scenario whereby someone got simple data set, and the first point of call was deep learning. The moment I saw the report, the paper, I said, this is a wrong modeling. This is a very simple data. Why you started with deep learning, they were able to achieve, I think, 75% or thereabout. So I said, why deep learning? Because it is in vogue. Oh, deep learning everywhere. You need to understand the strong point and the unique characteristics of each of the modeling algorithms. If you are dealing with videos, with pictures, deep learning has that capability to extract feature automatically from the data set without any human intervention. What we are used to in normal modeling is for human being to extract the data and then we supply it to our machine learning algorithm. However, with the coming of deep learning, that is why you use it in autonomous vehicles. You want to take as many videos as the vehicle is going to be able to direct the vehicle what to do, whether to stop, somebody is crossing or not. So we can't afford to say, okay, let's just get the data and go home and remove the feature. We need the feature in real time. Deep learning perform wonders in these scenarios. So we use them to extract. As I'm talking now, you see, the AI algorithm is picking my voice and converting it and making a summary of our lecture. See, this is a real-time feature extraction. It's taking my voice, it's extracting features from my voice, and then using it to generate translation or transcript, as the case may be. This is where you need deep learning, when you have to do real-time extraction of features. But when it comes to ordinary data, in fact, we have seen that after the deep learning finished the extraction of data, so we were explaining the idea of hyperparameter optimization, and then the need for us to select algorithms starting from the simple to the complex one. Start from the simple to the complex. We don't just jump to big algorithms. We may miss insight, just like the example I was given, that a deep learning used on a simple data may not be able to correctly model the data. Meanwhile, when we use k-nearest neighbor, we were able to achieve 95% better than what the deep learning achieved. That is the big principle I want us to move with if we really want the data to speak. And that is the principle of letting the data speak. So that we need to be aware of that. So once you have checked the first algorithm, simple one, you try another algorithm, you can keep changing the algorithm, simple one, simple algorithm. Don't go to ensemble yet. It's not yet time for that. Keep trying simple algorithms. After you have tried all these, then you start thinking that, oh, I think I still need better result. Because I say keep trying until the result is better. Satisfy what your client needs. So at this point in time, okay, so at this point in time, we may then go back. One of the very popular pre-processing that we can try, after you have tried some of the simple algorithm, we still have There are still other things you can check out. You can try to do ensemble, but usually we don't do ensemble quickly because ensemble takes a lot of time. So at this point, you can go back. You can go back, not going back here again. You can go back all back to the data stage, data preprocessing. See, one of the things you can start to look at is maybe there's outlier in my data. Maybe there's outlier in my data. One very common one is maybe data transformation. Let me carry out normalization of my data. Let me normalize my data. This is another big mistake people do make. The moment they get the data set, they normalize it before running the first modeling. This is wrong. Why? Because we've seen cases where normalized data did not give you better result. In fact, it was after they try, they brought it to my table, and then I said, where's the original data? Because looking at the data, I know it's normalized. I said, where's the original data? They brought the original data. I said, okay, use the original data, let me see the result. And they found out that they got better result than they were getting in normalized data for. So the idea of letting the data speak, we are presenting here, doing it right, is to always compare. So the result of the first initial modeling we have done, without normalizing the data, make sure you record it there. Put it there. Now go back and normalize your data and then come in again to the modeling stage. Do your modeling, check the performance. Put the result of normalized data and non-normalized data, put them side by side. Put them side by side and then see which one is getting better result. And then we still have a lot of other options that we can actually look at. So this is how the principle should be approached. So because of our time, I think it's a good time to stop now in case there are a few questions or questions to answer. And hopefully next time we still continue with this idea, try to expose us to how to do it right. Very, very important. So that we don't miss the insight that are inherent in our data set. And by doing that, we're going to ensure that we are letting the data speak without missing useful insight. So thank you very much for listening. So we're going to take some question time if there's, thank you very much, or comment, as the case may be.